Welcome to Engineered for Impact, a show helping engineers learn and think more about how they can have a positive social impact with their career. In this episode, I talk to Juan García Martínez, a chemical engineer and research manager at the Alliance to Feed Earth in Disasters, or ALLFED. ALLFED's mission is to increase the world's resilience to global food shocks that might be caused by a global catastrophe. So in this episode, we discuss what resilient foods are and the scenarios in which they may be essential for saving human lives, how single-cell proteins can be scaled up as a food source in a global catastrophe, some of the short-term uses of resilient foods, the preparedness of governments for catastrophic risk and how ALLFED's research is being translated for policy applications, and examples of technologies that ALLFED is currently working on and their volunteering program. You'll find show notes with valuable resources related to this episode at engineeredforimpact.show/Juan. That's Juan. If you enjoyed this episode, please leave us feedback on the website and share the episode with a friend or colleague. So, without further ado, here's Juan.
Yeah, so I'm Juan García, chemical engineer from Spain. I'm now working as research manager at ALLFED, the Alliance to Feed the Earth in Disasters. And we work there to, our mission is to increase humanity's resilience to global catastrophic food shocks, increase the resilience of communities, governments, and institutions to things like a nuclear winter or a collapse of critical infrastructure that causes a significant reduction in food production and distribution. And I'm also working as, I co-founder and a bit of co-director of the Riesgos Catastróficos Globales, an organization working to do science policy translation to get policy recommendations from the literature in existential risk and global catastrophic risk to policymakers and decision makers.
Terrific. Well, thank you for joining me, Juan. I'm very excited to get to discuss some of the work you're doing at ALLFED and the organization that you've co-founded. But first of all, I wanted to sort of understand how you got from studying chemical engineering to be working at ALLFED and becoming interested in global catastrophic risks.
Yes, so I would say the root of all this was my interest in climate change, which had been a thing since very early in my life. And when I was studying chemical engineering, that was certainly a big thing in my mind, especially as we started getting more autonomy, towards doing the bachelor thesis and so on. I started looking for ideas on what I could do to help solve the problem to some degree. And I, at the same time, got introduced to the 80K podcast, and some of the ideas like the NTI, like the framework of like neglectedness, tractability, and importance of a problem. And that was a big thing for me at the time. I decided to start working on renewable energies and other technologies to fight climate change. And I started with my bachelor's thesis on developing an alternative, more efficient process to produce solar-grade silicon for building photovoltaic cells. Just at the student level and exploration. And then I started reading more and more about it. I started getting more interested in the tail risks of climate change, the end of the curve where like the most extreme consequences lie, basically the worst possible climate future, right? And that was the beginning of the root of this interest, you could say. As I went forward, I started worrying more about other causes like animal suffering. I started looking into alternative proteins under development, like cultured meat and other pillars of the alternative protein industry, as a way to try to address both the challenges of solving the problem of animal suffering and climate change. And that's what I was trying to do at EAG 2019, network with the alternative protein people, when I met the team at ALLFED, from which I had already heard in the 80,000 Hours podcast. And I really liked the research. I saw their scientific posters. I saw they were doing real work, and specifically real chemical engineering work. So I decided to volunteer, and that's how I got here today.
Awesome. Yeah, I think we've got some similarities in that ALLFED was sort of, when I came across them also through the 80,000 Hours podcast. I think the second episode they did with David Denkenberger, that was the first time that I really saw sort of something that looked like direct engineering work being done in this context of trying to solve the world's most pressing problems. So it was definitely something that captivated my interest, and obviously yours as well. How does your other organization sort of fit in with this journey?
Right. So the idea for that came to us like over a year ago, where we started seeing, like, it was mostly inspired by looking at what governments had done in response to COVID, as an inspiration as to what they might do against other catastrophes like the ones we're studying at ALLFED, which got us a little worried about the capabilities of institutions to respond to these things, and how behind they were on incorporating expert recommendations in preparedness and resilience against extreme catastrophes. And we started thinking about like why that might be and why they're particularly bad at doing that for the more extreme the catastrophe is, for like low probability impact risks. So eventually we started doing interviews and work with civil servants and policymakers and so on, people from national security. We wrote a report on it. And I've been, that started my transition from just GCR and X-risk research to also a bit of policy work. And eventually we decided to ramp that up to a separate organization to try to act as knowledge brokers or science policy translators to see if we can get a higher uptake of the recommendations in the literature from, researchers in the space towards policymakers.
Yeah, that's really interesting. I want to circle back to sort of how governments respond to like ALLFED and your communications around actually trying to prepare for these catastrophic scenarios. But I think before we do that, could you perhaps introduce what resilient foods are and the kind of scenarios in which they might be essential to reduce life loss during specific catastrophes?
Yes, I could talk about this for several hours. I'm going to try to be concise. Resilient foods, I would say, are a set of solutions for food production and distribution that one can apply when there has been a huge loss of food production. And they include things such as interventions like redirecting human edible food from current uses to like biofuel production or animal feed for, say, meat or dairy production, towards direct consumption by humans, which in some countries is very significant. Like they produce way more food for animals and biofuels than for humans. That's one big. Those are some big ones, and then there's other alternative food production methods that could help us cover the gap in yields when there's been a catastrophe. So the type of catastrophes I'm thinking about now are things like what we call an abrupt sunlight reduction scenario, which is a scenario in which a significant amount of aerosol materials gets thrown into the atmosphere and gets lost into the upper atmosphere where it can be rained down. And it reduces the amount of sunlight that gets through and reaches the surface of the earth, reducing temperature and precipitation and the sunlight that the plants need for photosynthesis. And this could cause massive crop failures. That's one scenario. Another scenario is what I call a collapse of critical infrastructures. You lose industry, electricity, finance, water supply, and all of the other infrastructure sectors. To some degree, it's all interconnected. It's now in our society all there could be like cascading, like a domino scale type of thing. And if we were to lose some or many of them simultaneously through, for example, nuclear electromagnetic pulse or an extreme solar flare, that would cause a significant loss of food production because it would reduce the agricultural machinery, pesticides, fertilizers, a lot of the things that we need now to produce food. And it could also be combined with the other scenario, with the sunlight reaction scenario. For example, in a nuclear war, which could cause a nuclear winter, which is one very concerning abrupt sunlight reaction scenario. You could also have nuclear electromagnetic pulse attacks that will also destroy infrastructure through vast areas globally, or even a coordinated nuclear EMP attack that could affect easily the entire Earth with not that many weapons. So that's the most concerning scenario, the scenario where both of these things happen simultaneously, and then we lose both a lot of the sunlight and a lot of the agricultural inputs, right? Now, these are the type of scenarios that we have in mind where resilient food solutions will be most useful, although they can also be applied to smaller shocks, like, say, losing 10% of the global food production from like climate change-induced multiple breadbasket failures and so on. Our work is about identifying the potential of solutions like the redirection of human food, like that I described earlier, and also the production of resilient foods like rapid deployment of seaweed production facilities, which would still be able to grow in a nuclear winter or with limited technological materials in a collapse of critical infrastructures, right? They grow very fast, even in extreme scenarios, so that's why they're very useful. We could relocate crops to crops with a higher yield, or crops that work better in different climate conditions after the catastrophe. Like cool tolerant crops, for example, relocating them to new climate areas after the catastrophe where they can now be grown, say, moving them from northern latitudes to more tropical or southern latitudes where the climate is better after the catastrophe, and then like maybe sending the produced food back and distributing it. I'm also talking about things like industrial food production, like making use of the industrial infrastructure that we have today through repurposing and the deployment of rapid construction of factories. Think of like repurposing paper factories or breweries or biorefineries from whatever they're doing now to converting lignocellulosic biomass like woods, trees, leaves into lignocellulosic sugars that we can eat, or protein derived from those sugars through fermentation. And the deployment of factories like to convert gases like methane, biogas, natural gas, CO2 and electricity and other inputs from something that's completely inedible to single-cell protein through fermentation. And the single-cell protein is very high in protein content. It's got very high digestibility, very good amino acid profile. So like it's not low quality food. It's something that could be very useful in a catastrophe. Other than that, I'm just mentioning like the most important ones that we've been working on, but we have a very long list or very long portfolio. There's also like decentralized solutions that can be done at the community scale, like extracting protein from non-toxic leaves, or using wood that's lying around to produce mushrooms, or agricultural residues to produce dairy. You can also deploy greenhouses to make better use of the sunlight that's left in the sunlight reaction scenarios. That's some ideas to give you a flavor. So the way our work is like we assess the potential of these through high-level mathematical assessments, like modeling. Then we put it all together, we see what makes the most sense, how they compete with each other for resources, and can be used to respond to the catastrophe. We do scenario modeling in this way. We're also working on like economic assessment to try to see the affordability of these foods in different scenarios, how they could be deployed, what degree of deployment of each of these things is necessary and feasible in different scenarios. And other work that we're doing, other than basic research on these, evidence generation, we have translation, again, from science to policy. We're working on reports that we are publicizing among decision makers in various governments with the high-level policy recommendations that have stemmed from our work to try to get them to create resilience in the world today through R&D, targeted investments, preparedness, preparation of response plans, legislative change, and so on. And not only to create resilience, but also to put in place response plans with actions that will be required post-catastrophe. And finally, we're also working on technology R&D to develop like technologies that would help with critical bottlenecks when rapidly deploying the technologies that I'm just describing. We're doing some work on this. We would like to do a lot more. We're already working with some partners on this at universities who have access to labs. We are fundraising to develop a lot more of these technologies to again address critical bottlenecks. So those are some of the ways that we're working on to through these technologies and this research create resilience in the world today.
Yeah, awesome. There's definitely a lot that ALLFED does across this broad spectrum of all the way from evidence generation to translating that research into policy actionable information. I guess as a starting point, are you able to elaborate a little bit on what some of the technologies that you're currently working on to address some of those bottlenecks or other technologies?
Yeah, of course. So as a chemical engineer, most of my work has focused on the industrial solutions. I have been writing a lot of scientific publications on this topic, trying to assess like mostly the technologies that had to do with industrial factories. How fast could we deploy them and scale them? How ready are they to be deployed quickly at this moment, and how can we make that more likely to happen, more from the world we are now to the world where we can effectively and quickly deploy these? What is the cost of deploying these technologies? What are some bottlenecks in terms of inputs, resources, labor that we might find when trying to deploy them as quickly as needed in these scenarios that will start having an impact just a few months after they have happened and will last for years, up to a decade or so. So that includes things like, doing techno-economic analysis and net present value analysis to estimate production costs, selling prices for things like lignocellulosic sugar, single-cell protein, fat synthesized from petroleum byproducts or from CO2, microbial fats or synthetic fats, other foods produced from CO2 through, for example, microbial electrosynthesis or electrochemical processes like artificial carbohydrate synthesis. So these are all of the things that I've been studying. Some of them on the context of, all of them in the context of responding to a catastrophe on Earth today. Some of them in the context of how can we use these CO2-based foods as a closed-loop food production system in extreme scenarios like an underground refuge with no access to the surface, or in the International Space Station as a way to maintain life support and food production systems. Because this could also help with the existential risk side of things, like just keeping a certain amount of people alive. So I've also done some work on that because it overlaps with how do we feed people on Earth in extreme catastrophes. I can go in as much depth as you'd like into either of these technologies. They're all very different and very interesting. But basically, the idea to respond to a catastrophe on Earth is we should collectively as a species be capable of deciding that we need to build very rapidly hundreds of full-scale, hundreds of thousands of megatons per year of foods like single-cell proteins, sugars, and other things in order to respond to a catastrophe of the magnitude that we're talking about, which is a reduction all the way up to 80-90% of current production, which would cause, with no response, incredible levels of famine, skyrocketing food prices. So that's most of what I've been working on the last few years.
I guess, are you able to explain the single cell proteins and sort of what the production mechanism for those are? Because in my sort of limited understanding, that seems like a relatively promising solution in a low sunlight scenario to be able to meet the protein needs of civilization.
Definitely, I'd love to. It's my personal favorite. So, single cell proteins are a set of protein-rich products based on single-cell organisms, which you can produce through different organisms and different processes and different inputs. I'm going to give some examples. Currently, some of them are already produced industrially, like nutritional yeast based on the organism of Baker's yeast, Saccharomyces cerevisiae. You can in bioreactors, fermenters, feed the sugar to a culture of microorganisms and have it multiply, and then you extract some of that and commercialize it. Another example is corn, which some people may have heard about, is used as a common meat substitute, one of the largest in the market right now and has been around for like decades. It is based on fungi, and they could produce it in airlift reactors and continuously and extracting some of it, separating it, and then post-processing it and texturizing it into something that resembles chicken meat. Those are some examples of what we have right now. The type of stuff that I'm studying for a catastrophe is a similar idea, but it's different in a way that makes it a better fit for the catastrophe. For example, I'm thinking mostly when I'm doing this of studying gas-based single-cell proteins, meaning that a lot of the most important inputs are gases. In these cases, what you need are four things, which is basically a general rule of thumb for cultivating microorganisms. You need a carbon source, a nitrogen source, an oxygen source, and an energy source. And with those four ingredients, you can cultivate these single-cell organisms, separate them, and then use them as food for people or for cattle or for other things. So to give you a couple of examples, the most highly promising, in my opinion, so far, according to the research I have done, is methane-based single-cell protein production. That is, for example, obtaining methane from natural gas or from biogas from anaerobic digestion, feeding that to the microbes as both a carbon and energy source. As you know, it contains carbon, and they incorporate that carbon into creating their own metabolism, and then they use it as a building block to create more of themselves. And they use the energy contained in the molecule, the same energy that you liberate when you burn it, right? In your house, for example, if you have a natural gas boiler, as the energy source for them to create their own materials. And then you need a nitrogen source. Typically, what is being used right now is ammonia, the same that they use to make fertilizers. You can use some of that as the nitrogen source. You can also use urea or other sources. And the bacteria incorporates that nitrogen into the proteins. As you know, you need nitrogen to make proteins. And then the last ingredient is the oxygen, which you can get directly from the atmosphere. You can separate it from the air. That's done at huge scales today. That's, I think, the most highly promising one because it seems to be the one that requires the least, say, capital and resources to produce. You need a bioreactor, dewatering to separate the solids, so the bacteria from the water in the medium, and some pretreatment equipment, but it's not as intensive as others. So I've estimated that one allows you to produce enough protein for the entirety of humanity in just a few years, I think 3-4 years. So within the catastrophe timelines that we're discussing here. Obviously, you don't want it to be your own source of food, but this is a measure of how high potential it is, right? This is just based on some capital investment models that I've been building, but I think it's a reasonable estimation. Other examples include, for example, the hydrogenotrophs rather than metanotrophs. So bacteria that eat hydrogen as their energy source and CO2, which can be from the air or from the CO2 that factories emit. There's no shortage of that, right? As their carbon source. And that way you need an electrolyzer to produce the hydrogen or a gasifier that produces the hydrogen and the CO2 from those sources or from the gasifier. You feed that into the reactor with a nitrogen and oxygen source, and it's a similar process to the methane. Then we've also studied that it seems more capital intensive. It requires more units because, for the methane, you already have a lot of methane extracting infrastructure, right? Natural gas producing infrastructure. But for the hydrogenotrophs, you need to put in place electrolyzers or gasifiers and so on. So those are some examples that I think would be high potential. The hydrogenotrophs are becoming popular these days. Lots of startups are popping out. I think the most famous one is probably Solar Foods. They're doing a lot of marketing around their product of we can produce protein from the air, right? Which is technically true, interestingly. they can. This is a way that you can do it. Get CO2 from the air. They really need to get the nitrogen from somewhere else. They can technically do it from the air, but it's very hard. Water from the air, you can capture vapor if you want, and the oxygen, as I said. So yeah, you can really get most of the 99% of the material you put in there from the air, which is pretty cool. And I think we're gonna see this. It's gonna be expensive, especially at first, but it's gonna be interesting as a new ingredient that's now being developed. That's only at the pilot scale. Currently, the methane-based single-cell protein is now at a stage where it can be commercialized soon. Just this year, the first large-scale, full-scale industrial food production built by Calista in China is going to start methane single-cell protein production. This is not science fiction; it's already happening. They're gonna turn it on real soon, if they haven't already, at a production capacity of 10,000 tons per year, which is very, very large. So I'm very interested to see where this is going and to see whether the final production costs will differ much from the ones I've estimated. I hope not.
Yeah, that's really interesting. I guess that it's a great way to be able to verify your estimations, and then hopefully you can, if there's anything off there, maybe you can refine it for the hydrogen based production method as well. Do you know what they're using the methane based single cell protein for in China?
At the moment, they are producing it to sell to the aquaculture industry as a very high quality feed for production of fish, possibly shrimp, I think, because they haven't yet gone through the whole ordeal of having it approved by food administrations. But that's already something they're working on. Not only them, but also their competitors. And everyone working in this space has shown interest in transitioning from aquaculture to human food, which is a higher value-added product, so it's in this interest, right? Yeah, so that's what they're using it right now, but very likely we'll see them trying to commercialize it for human food, just like Solar Foods is doing for the hydrogen-based one.
Yeah, it's really interesting. How much of a, I guess, motivating factor is short-term sort of uses for these more resilient foods compared to just building up some sort of capability in case there's a catastrophe? Because it seems like some of the most tractable solutions in this space could be the ones in which they've got shorter term, I guess, returns on investment, where you can actually get some amount of food production out. It can be used for cattle feed, for fish feed, and then I guess once we've got the capability set up, it can then be turned into something that can be used in a global catastrophe.
Yeah, I would say that for some resilient food solutions, you can divide into these two categories. The ones that will continue to be developed through market forces, because there's a return on investment to be had there, and others where that's not the case. In the first group, we have things like, some single-cell protein processes, like we've just discussed. On the other side, we have things like the sugar, the lignocellulosic sugar, which at the moment, sugar is dirt cheap to produce from sugarcane, so it's very expensive to get it through converting lignocellulosic biomass like wood and leaves. So that's why we're raising capital to try to make that happen, because for the ones that the market's already interested in, it's not as interesting. Although it's still interesting to raise capital to do experiments on how to do that faster, right? And that's something we're trying to raise money to do. But for the others, we need funding and work to do the actual technology development, so that we have the technology ready to go in case something ever happens. That's why we're also raising funds to try to have, for example, the repurposing of an existing paper factory, now that some of them are being closed, towards the production of sugar, to basically gain the insights that we need through these pilots to write a guide on how to do that, and how to do that for other factories worldwide at a large scale, so that we have the knowledge ready to go. So there's this division.
Yeah, that makes sense. And it seems like especially if you're applying the impactfulness, tractability, and neglectedness framework to these sorts of problems, that second category where market forces aren't going to ensure that technology is going to be developed, that second category is really important for organizations such as ALLFED to work on in that case.
Absolutely, and it makes total sense to try to widen the portfolio by making this into viable alternatives should something like a catastrophic scenario come to pass.
So in the case of like the sugar mills, that would be my understanding is basically taking paper or taking trees and pulping them and then ending up with sugar as the end product. And so the idea there would be to get in a factory and actually be able to do that conversion process. And then I guess would it be like open sourcing the sort of the learnings and publishing it and getting it out there?
Yeah, so briefly, an example of this is like paper mills already have a lot of the facilities that are needed for this. They basically have the entire pretreatment equipment installed there. So you can start from the pulp rather than from the base material, which already gets you a lot of the way through. So then you take this pulp and through either enzymatic process or supercritical physical chemical processes, convert that and break it down into its component monomers, basically break down the cellulose polymer into sugar monomers that can then be processed into a sugar product. And the idea is that we would like to do that at a pilot or some level, some scale, and write this open source guide on how to do that for the other factories and release that so that it's ready to be used in a catastrophe.
Right. And so you mentioned fundraising before. How much do you estimate that experiment costing?
It entirely depends on the scale of the factory that you're working with. For the repurposing, my estimations have varied wildly. At the smallest scale, if you're just like trying to do pilot experiments at like a small scale university plant, larger than lab scale, but still not industrial, the cheapest you can do it for is like a couple millions. All the way up to if you want to repurpose a proper large scale, full size paper mill, we're talking about like close to 100 million, $50 to $100 million. But we're still trying, especially now that there's some potential government funding on this for disaster preparedness.
Right. It seems like a lot of money, and I guess the question that pops into my head, given the sort of the magnitude of those figures, is how does it compare to other options or the next best option in terms of meeting food supply demands during a global catastrophe? Like, is there something specific about the paper mills that make them a real key piece to being able to feed everybody in a disaster?
This question is a lot more complex than it might seem at first. So we're trying to incentivize others, especially outside of the nonprofit community, to invest in doing this for various reasons. However, we think there are higher leverage interventions for philanthropic money within the space of resilient foods to do this type of work. We've scoped out a series of much lower cost technology development scales, on the order of magnitudes closer to like tens or hundreds of thousands of dollars that might address critical bottlenecks like rope twisting for seaweed production, because it would need to be scaled significantly in these catastrophes. Low-tech greenhouse open source development, crop relocation studies, simulating nuclear winter growing conditions, and a bunch of others. And those are the ones where we think philanthropic money can be best invested. In addition to the type of work that we're mostly doing, which is like high-level analysis to produce policy recommendations, disseminations, and policy translation. Those are like the lowest hanging fruit, highest leverage interventions. That's why we have been focusing on them. But we're also at the same time trying to make the others happen through other sources of funding. That's one way I could answer the question. The other way is we could talk about the costs and of each of the foods within the catastrophe scenario and the feasibility of scaling them. And that's one way that we rank the importance of some solution against others. That is why we have been focusing on like these most promising solutions, like crop relocation, seaweed deployment, methane single-cell protein, cellulosic sugar, greenhouses, and so on, because we think these are the ones that will be able to be deployed most quickly and at the lowest cost, so most affordable, which are the two main factors that we take into consideration as to how high the potential of resilient food technology is for responding to catastrophic scenarios. We call it the ramp-up speed, like how fast can you increase the production capacity, and the retail cost for consumers, because affordability is fundamental. In some of these scenarios, even if you're able to produce enough food, some economically disadvantaged populations will be priced out of the market, and that's something we want to prevent through producing low-cost foods, producing more foods than the bare minimum required to feed everyone, studying the feasibility of food aid and subsidization and so on, so that everyone has access to food if we do manage to produce enough food in these scenarios.
That makes a lot of sense. You previously said how the governments typically don't take the risks of food security from global catastrophes too seriously. Why do you think it is so hard to raise awareness about these sorts of topics when they do just seem, like on paper, they seem very, very important to consider, especially if you assume that there's a decent chance that there could be a global catastrophe that could reduce sunlight or drop global temperatures?
This is a very complicated question. It has to do with the policy appetite and priorities of policymakers, and how civil servants doing risk assessment see risk and think about risk. I could conjecture many things. One important piece of the puzzle, I would say, is that governments have very clearly a reactive policy in terms of risk preparedness. There's a pattern of ignoring expert warnings until it is too late, such as has happened historically with volcanic risk, like in the UK, and pandemics globally. What we need is more proactive resilience building and preparedness against not only global catastrophes, but disaster response in general. And this is something that people have been trying to build for a while. It's particularly bad the larger the catastrophe is and the lower the total probability is, because even though the probability and the impact make it so much more salient in terms of expected utility to deal with than other catastrophes, it still gets incredibly neglected. Like, it doesn't even get considered into government's national risk assessments. There could be various reasons for that. They could be unfamiliar with it. They could be simply rounding down the probability to zero, despite it being closer to 1 or 10%, right? Because they're more thinking of like, oh, but I know that next year I'm going to probably have a flood or a fire, whereas I don't know if I'm going to have a nuclear war, right? And there are other reasons, basically cognitive biases, making it hard for this to be addressed. They may perceive that there's a lack of policy options, like, well, this may be a problem, yes, but how do I deal with it as policymakers? I don't have any policies. And we're trying to deal with that, right, through work like we're doing at ALLFED and Riesgos Catastróficos Globales. So there are multiple possible reasons, probably a lot of them are at effect, as to why this is not being addressed right now. But I've become somewhat more positive about this in the past. I've been seeing interest from the UN in addressing these problems. I've been seeing more interest and appetite in local governments lately. So we'll see how that goes. So I've become slightly more optimistic in beating this like myopic perspective of like, ignoring the largest catastrophes that governments have had so far and just being reactive as to things that have already been happening.
Do you think that change in sentiment from governments has been influenced by the sort of the Russia-Ukraine situation and then COVID as well, and just with these catastrophes that are actually putting a bit of pressure now on the international food supply chain?
I think it's possible. Yeah, I think it's possible that some of these things have put a bit of a scare into some of the people that have capacity to do policy making in this space, and maybe that's making it easier to be heard. It certainly isn't making it easier to be funded by them, but it's at least probably making them more open to listen to ideas. So yeah, probably.
And when you're sort of interfacing with these government and regulatory bodies, what sort of engineering work are you taking to them? So like how does the sort of the engineering and the research and the sort of the evidence generation, how does that actually meet the policymakers? How do you translate that into something that policymakers can run with?
Right. Well, one obvious way is the writing of reports. As think tanks tend to do, we write a report, we publicize it, we move it around relevant circles, we collate as a collection. Yeah, we put together a collection of policy recommendations from the tens of published papers that we have published and also from unpublished analysis, putting together the highest leverage interventions, put them in a list of bullet points, followed by an explanation of why they would make sense in various different scenarios and to which degree and which ones have more potential and why. So this set of highest leverage interventions, we try to make sure that it reaches them. And then there are many ways that you can put it into effect. You can work to incorporate these policy recommendations into legislative text, and so that they do their own work in there, like so that they do targeted R&D investments, so that they establish contingency planning on their own, or aided by external experts like us and others. You can, for example, also write reports that they are interested in, like try to convince them through conversations like, well, you need a response plan for this. We can probably produce it for you if you're interested. That's another example. And then just more generally, people have been recommended things like pushing for more rational, rigorous, systematic, and inclusive national risk assessment for national risk registers that like incorporates the thinking and ideas from external experts and the public, so that it's done in a more transparent manner. Like people understand what assumptions are being used, why large catastrophes are being ignored or neglected, and that way making them more salient to them. And another way is to push for risk assessment policies that are more based on cost-benefit analysis rather than whatever they are based on at the moment, which is clearly not cost-benefit analysis. Those are just some ideas. At ALLFED, we're working on the first type, the reports and relationship building with institutions, companies, etc. The other type is more general GCRX risk policy type of stuff that is being done by that we're trying to do in Riesgos Catastróficos Globales for Spanish-speaking countries in particular. Other organizations are doing it in English-speaking countries like the Simon Institute or the Future Life Institute and others.
Right. Are there any sort of like systematic differences between English-speaking and Spanish-speaking contexts in this domain?
It's early to say because we've only been working on the Spanish-speaking country full-time on this for a few months. So far, it seems fairly similar in terms of the appetite for dealing with these and the interest that we've been seeing, and the way that they deal with the recommendations. So far, it seems fairly similar. It's just that we decided to start it because there was no one doing this in Spanish-speaking countries.
Yeah, it seems like the risk of, I guess, having quite centralized organizations doing, or having very few organizations doing this kind of work is that it can be restricted to a single language and even just like a single country or a single context where it's something that can benefit almost any country, any context, and that sort of
Absolutely.
translation needs to happen at some point.
Yeah. In my opinion, and I think I can speak for most of ALLFED's team here, uh, every single country in the world should have at least a contingency plan to some detail against the type of catastrophes that we're dealing with, which is clearly not the case right now. So yeah, we need to do work in English, in Spanish, in every single language.
Are there any countries that are like a gold standard for this at the moment, or is pretty much every country lacking in one way or another?
There's no gold standard so far. There are some countries that have invested a lot more into resilience, like the Scandinavian countries or Switzerland. They have like networks of refugees. They have very good disaster communications with like manuals for people on what to do in case of extreme catastrophes, to a much greater detail than a lot of other countries. But they still are not considering these extreme catastrophes and how to deal with the consequences and solutions to them to the scale that we're talking about at ALLFED.
Interesting. Are you able to talk about, I guess, some of the other engineering flavored technologies and ideas that you're sort of working on at ALLFED? Because I know there's quite a detailed list of project ideas that's floating around for like thesis, effective thesis ideas. And yeah, are there any on there that you would be, I guess, particularly excited to see people working on in one way or another?
Yeah, like you said, we have hundreds of research ideas. I'm now curating a database to make it easier for people who are interested in volunteering to choose a project, for us to make prioritization decisions. And I'm planning to publicize this in the EA forum when it's done, so that others can look at them and be like, oh, maybe I would want to work on this separately, right? So that will be published in this year at some point. Some highlights there could be, let's see. Well, it's not only resilient food-based stuff, but I can also talk to you about other civilizational resilience engineering projects if you're interested.
Yeah, definitely.
So some examples, I think some of them I've already mentioned, but things like simple greenhouse prototypes for fast scaling that can be done open source, rope twisters for seaweed, ideally also open source, plastic extruder for greenhouses, all of these trying to deal with some bottlenecks in the scaling in the extreme scenarios. Studies of seaweed or crop drying, because this would be an issue. Also, repurposing of industrial factories. Maybe at a smaller, more individual scale, we also have a list of ideas that I'll be incorporating into this database, including things like and crop growth experiments with artificial light, feeding, trying to produce bacteria from leaves. Some of these are more speculative. Producing, scaling up mushroom production from agricultural residues or leaves, wood, peat. Producing open source leaf grinders and other materials for the extraction of protein concentrate from leaves, and other open source materials for leaf protein concentrate production. Development of low-tech greenhouses, I already mentioned that, pilots, etc.
It sounds like there's a lot there that an interested engineer could just set up as a backyard experiment.
Some of them, yeah. For others, you actually need quite specialized equipment, and so are probably a better fit for PhDs at universities. But some of them, yeah. And I'm hoping to get some interest and uptake from like entrepreneurial individuals or just people who like to experiment with their own materials on this. So some other things that all of this stuff I talked about had to do with resilient foods, but we're also working on other civilizational resilience projects. It would be, for example, very interesting to get people with experience in telecommunications, for example, 4G, 5G protocols, with experience in development of Android apps, because we're also working on resilient communications projects through resilient satellites. And within communications, we're also working on what's it called? Like the idea of a decentralized shortwave radio network to keep communications in case of a collapse of infrastructure, communications industry, etc. And also, the proliferation of open source local production can help people lift themselves out of poverty and create pockets of resilience. For example, there's Open Source Ecology, is an organization working on this, and we've collaborated with them. And for people with experience in the power grid, we're also doing projects modeling electrical grid networks on a high-performance cluster. Whoever's highly motivated to help with that would be extremely useful to understand the cascading collapse of the power grid through, for example, like geomagnetic storms. So there's a lot more where that came from. So yeah, definitely a lot of ways that engineers can contribute to civilizational resilience.
Yeah, definitely. Perhaps it's a good time then to discuss ALLFED's volunteering program, and maybe you could outline sort of the state of the program at the moment, how people can get involved if they're interested, and some of the projects that you've maybe worked on recently with the help of volunteers, or are hoping to work on in the near-term future.
Yeah, so a brief overview is that this is a program we have been running for many years now. I think probably 4. Like I said, I myself started as a volunteer before joining as a researcher. And we now have a lot more people leading teams of volunteers than we used to. The way it normally works is you apply through our website, online form, and based on the information, we assess the people's fits to projects. Especially, we're particularly interested in people who can contribute to priority projects, but sometimes we also accommodate people who would like to start new projects. And then for those who we invite to join us in the research team as volunteers or on other teams as volunteers, we give a taster task, which is a bit like a small work task, just for us to see how you work and for you to see whether you like the kind of work that you'll be doing with us. And then you get incorporated to a project. And some of the projects that I'm running with volunteers at the moment include the creation of a technology readiness level frameworks for resilient food production technologies, or single-cell protein production from wood, or a nutritional analysis of resilient food combinations and diets. Some projects that we're interested to get more volunteers for, especially people with extensive expertise in these topics, include things like the rapid repurposing of industrial infrastructure for microbial food production, single-cell proteins, single-cell fats. Again, microbial fat as a resilient food, assessing the combined production of lignocellulosic sugar and leaf protein concentrate in an integrated process. Single-cell protein from lignocellulosic biomass, like I said. These are the ones I'm working on. I'm taking volunteers for these. Others are working on things like modeling, crop modeling of outdoor growing of crops in a nuclear winter and relocation of cultural land plants. This requires people, with experience in crop modeling, DSAT, Python modeling, Linux, geographic information systems, and so on. Similar idea, modeling to study geomagnetic storms, solar storms. People developing open source materials for production of leaf protein concentrate, or for the access of water in a collapse of infrastructures. If water infrastructure fails, how do we get enough water to people in cities? Ground freezing in nuclear winter due to the sudden loss of sudden reduction in temperature. Those are just some of the ideas that we already have some people working on, and that we could get people to work on. That would be very useful.
Right. Yeah, that's really interesting. There's definitely a broad array of projects there that engineers from quite a wide range of backgrounds could work on. I've heard from quite a number of people at nonprofits who are running volunteer programs that they're deceptively difficult to run at times, and they can just be challenging to run effectively and get value for both the organization and for the volunteers who are actually giving up their time to do that work. What have you sort of learned from the difficulties that you've encountered over the last few years of running the volunteer program?
Yeah, as the main researcher working on the volunteer program, I can say that that's absolutely correct. It can be very hard to run an effective volunteer program, and you have to have the right work for volunteers for it to make sense. For example, there's been things where it's been a lot more challenging. It's been to bring volunteers on, like for programming work, complex modeling with like very large sets of code. It's been a lot harder to incorporate volunteers to do effective work there. Other things that might seem more similar to the type of like a master thesis or a PhD type of level work that you would do at university. It's been somewhat easier in my experience. I've had volunteers do great work, helping me in writing papers and writing analysis on some of these things. So you have to have the right tasks for people, I would say, is one big thing. We have the lack, or well, unfortunately, like there's not much work on this, and there's a lot of different analysis. Like I say, I have a huge database that I'll be releasing soon on this, and many of those are a good fit for volunteer work. Others not so much. But we have the lack that we have a lot of ideas that can be done through volunteer work, and that's why we've been running it successfully for so many years. Other things that you need to take into account, it's very hard to bring the right type of people in. We get lots of applications, and you have to develop a sense for who would be the best fit, who would enjoy volunteering most, who would become the most engaged, make the most useful work. Some ways we try to address this is we have a very in-depth form for volunteering where we try to gather a lot of information to give us an idea of what are the things that will make you the best fit for working on this type of projects. And we also have the taster task for that, as I mentioned earlier. I think it really helps having to reduce admin costs or management costs on our end, to have the structured process. I have, due to a limitation on the size of our team and how many people we can find salaries for, we have to have a limitation on how many people we can take in to manage as volunteers. So it helps to have a high bar as to who you bring in. I would love to bring anyone who brings a lot of interest, but sometimes that's not possible due to constraints in talent, funding, and so on. So it really helps to have a high bar, and especially in my experience, I would say selecting for people with high levels of autonomy, because those generally tend to make the worst volunteers, people who can work independently in a project. Even though I have it's very common for us to have weekly meetings with volunteers in projects, but you have to find the people with the capacity to actually do work in between those periodical meetings. And especially also selecting for people with larger weekly time availability. That's a pretty obvious one, right? Those are some ideas that can help people run a more effective volunteering program.
Right. And so you've obviously had quite a number of engineers come through the volunteering program, and I imagine as well, just by the nature of ALLFED being one of the very few, I guess, visible organizations who are doing engineering-based work in sort of the impact-focused space. Is there advice that you often find yourself giving to engineers who are looking to increase their impact?
This question I tend to get a lot at the AG conferences. So a large part of the answer I tend to give is on the lines of stuff that we've talked about, like, well, here are some projects that are engineering related that you can do to contribute to the field of civilization or resilience. There are other work that you can do to have a high impact as an engineer. For example, this is something I've thought a lot about for chemical engineers. So some recommendations I tend to give to chemical engineers, other than doing civilization or resilience work, not only for like global catastrophic food shocks, but you can also work in pandemic resilience as an engineer. Other than like more global catastrophic risk type of stuff, you can work on obviously alternative protein and cellular agriculture. There's a lot of chemical engineering expertise needed within the fields of cultured meat, plant-based meat, fermentation, whether it be biomass fermentation or precision fermentation. It needs a lot of chemical engineering talent, and it seems to be, according to what the people in the industry is saying, there is a shortage of talent there. So I encourage more chemical engineers and more engineers in general to look into that always. And then other things that are a little bit more crowded but still important is stuff like sustainable process technology, renewable energy research, entrepreneurship. Within the field of like lower negative emissions technologies, the R&D of CO2 capture and conversion, circular economy, engineering projects, things converting like waste to products. A lot of things tends to fall into this category. And yeah, just entrepreneurship in general seems to be a bottleneck. So if you can develop the career capital to work on these things and address these bottlenecks, like entrepreneurial management capacity or very niche engineering research, then that's a good way to have an outsized impact as an engineer.
Nice. Have you seen examples or got any like tips for people who want to follow that sort of smaller R&D entrepreneurial pathway? Given that there are quite a number of ideas you've mentioned throughout this discussion that could sort of fit that bill of technologies that could, in theory, be developed into something that's a bigger commercial enterprise or R&D project?
This one I don't have a clear response to. I guess what I could think of is for people looking to work on something like this, one recommendation would be to start getting more familiar with new technologies within this space. Start following companies and their newsletters, LinkedIn, who are developing these technologies that you might be interested in, or zero in on a problem and see which technologies can address it, and ideally, which one can address it on a larger scale, right? So I'm thinking, like, for example, if you're interested in single-cell proteins to address like animal suffering and climate change and so on, or alternative proteins, follow companies working in this space, and then try to join, like for early career people, I would recommend that they join like startups on these to develop the career capital necessary to ideally later do their own entrepreneurial project or do their own research based on what they did, or do the same but at a university, right? There's a lot of pioneering researchers working to do this outside of industry that can then help you develop the knowledge required to jump into industry or do your own work. So that's one way to answer, I suppose.
Yeah, awesome. Is there anything else you would like to mention?
Probably an important message here could be that for the type of catastrophes that we're talking about at ALLFED, there is hope, and there are things that we as a species can do about it to survive and to make it through it. And in an individual level, the things that make the most sense are far from starting prepping, right? It looks more like starting to do more work and research in this field, maybe at a university or through volunteering with us or other projects working on this type of field, or donating to organizations working on this. Another interesting, important message is that we worry that in these scenarios, if governments and individuals are not aware of resilient food solutions, they might think that most people will starve no matter what you do, which is not true, as our analysis prove. And this might take them to do zero-sum actions like invading their neighbors. But if we could get the message out in time, if something like this ever happens, that we can feed everyone through technology response, international cooperation, trading, then our chances of as a species getting through this are much, much better. And finally, I would stress that for these and other complicated projects and problems related to engineering and climate change and global catastrophes, I would like to highlight the importance of an interdisciplinary mindset. A lot of the work that we're doing at ALLFED cuts through so many disciplines that we tend to have a team where like each person has a different background and idea of how to solve the problem, and that's what gets us through a novel solution. And a solution is mindset in the sense of like not being too optimistic about technology, it can't solve every problem, but also not being too pessimistic about the problems and considering that they're unsolvable. Just look at the challenge in the face and try to develop solutions for it. That's what we call solutions mindset. And that's a framework that I quite like. And scalability, important in these catastrophes and any other problems. Developing scalable solutions, that's all that we're about. And flexibility in disaster response, especially in the part of governments, disaster response organizations, and so on. They should have the capacity to respond flexibly, the adequate stockpiles, the adequate contingency planning, to respond to not only this type of catastrophes, but all types of catastrophes. And that's already a lot.
Yeah.
So
yeah, I think one of the things that I really came away with after listening to the 80,000 Hours podcast with David was actually a sense of hope about this. I think prior to that, I was quite concerned about what would happen if we had, even without a catastrophe, just like a couple of bad years of weather or some sort of other event which caused major bread baskets to fail or some sort of food system breakdown. Just how fragile that would be and how distressing and potentially catastrophic that could be on its own. And I think, after I listened to that episode, I had a lot of hope about there actually being a very good chance that things would be okay, and that there is actually we do have more resiliency there if we're prepared for it. And I shared it with quite a few friends on the back of that as well, just because a few friends who were feeling pessimistic in the same way, I think took some value out of hearing the hopeful message that sort of came through from the work that ALLFED's been doing.
That's a nice reflection. And I would add that in order for us to move to the world in which that optimism is well justified, there's a lot of work that needs to be done, both in terms of technology development, on work with governments to establish preparedness. If we do manage to pull this through, we will be in a much better position. But it requires a lot of tough work and continued so that we continue to have the capacity to respond to these.
Speaking of, David Denkenberger is now located in New Zealand at the University of Canterbury, I believe, and he's looking to bring on some PhD students. I was wondering if you could elaborate on some of the topics that the PhD students might be able to work on.
Yeah, so some of the topics he's mentioned include analyzing satellite communications with regular cell phones, like I related to the satellite project that we mentioned before, cost and scale-up capability of high-tech greenhouses, not only the low-tech greenhouses that we've been studying, repurposing paper factories to protein and sugar production, impact on the energy system of the type of catastrophes that we're talking about, for example, a nuclear winter, how would that affect energy production? For the collapse of critical infrastructures, interventions to recover infrastructure quickly to prevent the catastrophe from becoming very protracted. cost and scaling analysis of seaweed and how to deploy it with reduced infrastructure and reduced sunlight in these like combined scenarios, providing home heating in electricity collapse scenarios, logistics of food and feedstock transportation more generally, some projects on that. Those are some examples.
Yeah, awesome. There's definitely a broad range there for quite a number of disciplines yet again. What are your top 3 resources for people who want to learn more about resilient foods?
So for a general public and as an introduction, I like the text that we wrote for our website. We have a section called Resilient Foods. That's very interesting and very accessible. Also, we have a lot of presentations on YouTube. If you just look up ALLFED presentation, like a presentation for EAGX and for other conferences. Those are also good introductions. For more in-depth material, I can recommend, we have the publication section on the website. I would recommend there, for example, as an introduction, our paper in nutrition in sunlight reduction scenarios. It's a pretty good introduction to the academic material, and our integrated model paper, which is called Food System Adaptation and Sunlight Reduction Scenarios, something similar to that. And finally, I am a fan of our reports that we have been writing for governments in strategic planning and contingency planning. Those are not yet published, but they are upcoming. We'll soon be putting them out. And those would give you like a good idea of like, here are the things that you need to do as soon as a catastrophe happens. Could be very interesting reading for some audiences.
Yeah, that definitely sounds interesting. I'll have to get those links off you when they're published, and we'll put them in the show notes for anyone who's coming back to this episode a little bit later down the track once those are published. What do you wish you had invented, and why?
Yeah, that is a hard one. I'm sure I could, with more time, come up with a better answer. I wish I had come up with the idea of producing proteins from the air. The very clever people in NASA in the 60s did that through arguably out-of-the-box thinking to a very high degree of like, well, how do we feed people on space, right? What are some ways that we could produce food on site so we don't have to launch as much food stocks? And then they developed this whole system to scrub the CO2 from the aircraft atmosphere and a bunch of other materials, and try to make as close that loop as possible so that they don't have to take as many food stocks. That was fascinating read, all the way from the original documents in the 60s to the papers that are being published right now. I continue to be fascinated by that. That's. I really wish I had been in the original team there and lived through that discovery.
Yeah, it's pretty awesome that that's sort of 60 years in the making, and there's now only just, this a couple of organizations who are starting to produce those products at hopefully a proof of concept for commercial scale. It's, I guess, a testament to just how challenging and tricky some of these ideas are.
Yeah, there's one of those ideas that was just waiting for its time, right?
Yeah, definitely. Well, where can people find out more about you, more about ALLFED online?
Well, for ALLFED, the best resource is the website, allfed.info, where you can read the material, apply to volunteer in the Join Us section, check out our publications. For me, you can easily find me on LinkedIn. If my name there is Juan B. García Martínez. Happy to connect with people. Feel free to check out also my presentations on YouTube. I also have a channel that I am slowly but surely uploading more material to. Those are the best ways.
Fantastic. Well, Juan, thank you so much for joining me today.
It's been a pleasure. Thanks, Sean.
I hope you enjoyed that conversation with Juan. For detailed show notes and links to learn more, please head to engineeredforimpact.show/Juan. That's JUAN. If you would like to support the podcast, the best thing that you can do is to leave us feedback. We're continuously seeking to improve the quality of the podcast and increase the value that it can provide you. So by leaving us feedback on what you'd like and don't like about the episodes, we can make it a better podcast. You can leave us feedback by heading to the show notes page for this episode. Thanks for listening, and happy problem solving.